Welcome to our lecture on digital technology with VHDL. Today, we will explore the fascinating world of digital systems and how VHDL plays a crucial role in their design and implementation. In this lecture, we will cover three main topics: course information, the digital number system, and number conversions. Let's dive in and start with the course information. Our first topic is number systems. Understanding number systems is fundamental to grasping how digital technology works. Digital systems are everywhere, from mobile phones to microwave ovens. These systems manipulate discrete units of data, represented as alphabets or binary digits. Binary digits, or bits, use only two symbols, 0 and 1. Each bit can be combined to form words, similar to how letters form words in natural languages. Bits can represent various states, such as on or off, open or closed, and high or low voltage. These combinations are the building blocks of digital communication. Humans use alphabets to communicate, while computers use bits. These bits are organized into words, stored in registers, and communicated over a bus. All data must be in binary form for processing. Analog data must be converted to binary, and the data representation must be in the appropriate number system. This graph illustrates how analog data is converted to binary form. Proper data representation is crucial for accurate processing in digital systems. Number systems are used in arithmetic to represent numbers by strings of digits. There are two main types: positional and non-positional. In positional number systems, the value of each digit depends on its position. Non-positional systems, like Roman numerals, do not rely on position for value. Let's explore the two types of number systems in more detail: positional and non-positional. Each has unique characteristics and applications. An example of a non-positional number system is Latin numerals. The value is determined by the digits' position relative to each other, with specific rules for addition and subtraction. Latin numerals use specific digits to represent values. For example, I represents 1, V represents 5, and X represents 10. These digits are combined to form larger numbers. Let's look at some examples of Latin numerals. For instance, XL represents 40, and MCM represents 1900. Can you determine the values of CCLXI and CCLXVI? In positional number systems, the value of each digit depends on its position. These systems are expressed in a base or radix, which can vary. Positional number systems can have different bases, such as base 2, base 6, and base 10. Each base uses a unique set of digits to represent values. Here are more examples of different bases, including base 8, base 13, and base 16. Each base expands the range of values that can be represented. To represent any number A with radix r, we use n digits before the radix point and m digits after the radix point. This method allows us to accurately represent numbers in various bases, ensuring precise calculations and data representation in digital systems. We can represent any number A with a radix r, where n digits come before the radix point and m digits come after it. The radix, or base, of the system is r, and every digit A_i ranges from 0 to r1. The digit set includes all possible values for these digits. The radix point is crucial in our number system. In base 10, it's called the decimal point. The digit A_n1 is the most significant digit, while A_m is the least significant digit. Number n in radix r can be expressed as a power series of r, with each digit multiplied by r raised to the power of its position. This power series representation helps in understanding the value of each digit in the number, contributing to the overall value of n. For example, a underscore n1 asterisk r caret, n1, plus a underscore n2 asterisk r caret, n2, and so on, until a underscore m asterisk r caret, m. This formula helps in breaking down the number into its components. In digital electronics, we often use binary, octal, and hexadecimal systems for convenience. Each system has its own base and digit set. In the binary system, the base is 2, and the digits are 0 and 1. This system is fundamental in computing and digital logic. The octal system uses base 8, with digits ranging from 0 to 7. It's often used in computing as a more compact representation of binary numbers. The hexadecimal system, with base 16, uses digits from 0 to 9 and letters A to F. It's widely used in programming and digital electronics. Let's look at an example. The binary number 0.101 represents 0.5 plus 0.125, which equals 0.625 in decimal. For octal, the number 11,100.10111 converts to 28.71875 in decimal. This involves multiplying each digit by 8 raised to the power of its position. In hexadecimal, the number 1CB8 converts to 28.71875 in decimal. Each digit is multiplied by 16 raised to the power of its position. By understanding these conversions, we can see the connections between binary, octal, and hexadecimal systems, making it easier to work with different bases. Let's explore the connections between binary, octal, and hexadecimal number systems. To convert binary to octal, group the binary digits into sets of 3, adding leading or trailing zeros if necessary. This intermediate step simplifies the conversion process. Similarly, converting binary to hexadecimal involves grouping the binary digits into sets of 4. Again, leading or trailing zeros can be added to make the groups complete. This method ensures a smooth transition between binary and hexadecimal. To convert from octal to hexadecimal, first convert the octal number to binary, then from binary to hexadecimal. This two-step process leverages the simplicity of binary conversions to achieve the final result. Converting from any radix to base 10 is straightforward using a specific equation. This equation helps in understanding the relationship between different number systems and base 10. To convert from base 10 to any radix, division is used. By repeatedly dividing the number by the radix and keeping track of the remainders, we can achieve the desired conversion. Let's see an example of converting the integer part of a base 10 number to binary. We start by dividing the number by 2 and recording the remainders. Continuing with our example, we divide the quotient by 2 again and record the remainder. This process is repeated until the quotient is 0. As we proceed, each division step brings us closer to the final binary representation. The remainders form the binary digits from least significant to most significant bit. We continue dividing and recording remainders, ensuring each step is clear and methodical. This systematic approach guarantees accuracy in the conversion process. With each division, we are constructing the binary number bit by bit. The remainders are crucial as they represent the binary digits. Finally, we reach the last division step. The remainders collected from bottom to top give us the complete binary number. The final binary representation of the number 57 is 111,001. This example illustrates the effectiveness of the division method for converting integers from base 10 to binary. Now, let's look at converting the fractional part of a base 10 number to binary. This involves multiplying the fraction by 2 and recording the integer part of the result. In our example, we start by multiplying 0.625 by 2. The integer part of the result is recorded, and the fractional part is used for the next multiplication. We continue multiplying the fractional part by 2 and recording the integer parts. This iterative process is similar to the division method used for integers. As we proceed, each multiplication step brings us closer to the final binary representation of the fraction. The recorded integer parts form the binary digits. Finally, we reach the last multiplication step. The integer parts collected give us the complete binary representation of the fraction. The final binary representation of the fraction 0.625 is 0.101. This example demonstrates the effectiveness of the multiplication method for converting fractions from base 10 to binary. Understanding the range of numbers in a given radix is crucial. For a number with n plus m digits, the largest integer is r⁻n1, and the smallest integer is 0. This defines the integer range in the given radix. Similarly, the range for fractions in a given radix is defined. The largest fraction is 0.0, and the smallest fraction is 1r⁻m. This defines the fractional range in the given radix. Given numbers n1 with n plus m digits in a radix R number, the largest integer in n1 is r⁻n1, and the minimum integer in n1 is 0. The integer range in n1 is from 0 to r⁻n1. The largest fraction in n1 is 0.0, and the minimum fraction in n1 is 1r⁻m. The fraction range in n1 is from 0.0 to 1r⁻m. The number range in n1 is r⁻n1 to 1r⁻m equals r⁻n1 plus 1r⁻m equals r⁻n⁻m. For example, with r equals 10, n equals 3, and m equals 3, the largest integer greater in n1 is r⁻n1 equals 10 to the power of 3 1 equals 999. The minimum fraction in n1 is 1r⁻m equals 10.001 equals 0.999. The largest number in n1 is r⁻n1 plus 1r⁻m equals 1000 0.001 equals 999.999, and the minimum is 0. Another example with r equals 2, n equals 3, and m equals 3, the largest integer greater in n1 is r⁻n1 equals 2 to the power of 3 1 equals 7. The minimum fraction in n1 is 1r⁻m equals 10.125 equals 0.875. The largest number in n1 is r⁻n1 plus 1r⁻m equals 80.125 equals 7.875, and the minimum is 0. A bit is the smallest binary quantity, containing only one digit from 0, 1. Hence 2 to the power of 1 possible combinations of bits 0 or 1, and n equals 0. The largest number is 1, minimum is 0. A byte is a string of bits from 0, 1, n greater than 8. N is preferably integer multiples of 8. N equals 8. I equals 2, 3, 4. Hence, 2⁻n possible combinations of bits are r equals 2, n equals 1 and m equals 0. The largest number is 1, minimum is 0. A bit is the smallest binary quantity, containing only one digit from 0, 1. Hence 2 to the power of 1 possible combinations of bits 0 or 1, and n equals 0. The largest number is 1, minimum is 0. A byte is a string of bits from 0, 1, n greater than 8. N is preferably integer multiples of 8. N equals 8. I equals 2, 3, 4. Hence, 2 caret n possible combinations of bits are r equals 2, n equals 1 and m equals 0. The largest number is 1, minimum is 0. A word is a string of bits containing n digits from 0, 1, n greater than 8. N is preferably integer multiples of 8, n equals 8, I equals 2, 3, 4. Hence there are 2 caret n possible combinations of bits in a word or r equals 2, n equals 8, m equals 0 and n equals 4. The largest number is 2 caret n 1, minimum is 0. Unsigned binary numbers only include positive numbers. All the bit locations are used in expressing the value of the number. Signed binary numbers can be both positive and negative. The leftmost bit specifies the sign of the number, with 1 for negative and 0 for positive. Digits after the leftmost bit represent the value of the number. Standards for determining the value of a signed binary number include sign magnitude representation, where the first digit is the sign and the rest is the magnitude. 2's complement representation, where for n_r, n integer digits, 2's complement of n_r is 2 caret n_r. 1's complement representation, where 1's complement of n_r is 2 caret n1, n_r. In sign magnitude, n_r equals 00010001. Sign is 0, plus, magnitude is 001001, plus 17, 10. In 2's complement, n_r equals 00010001. R equals 2, n equals 8. z_r equals 10 million. n_r equals 10,000,000100001 equals 11,101,111. A simple approach to 2's complement is to invert the number and add 1. For example, n_r equals 00010001. Inverse n_r equals 11,101,110. Add 1 to get n_r equals 11,101,110 plus 1 equals 11,101,111. In 1's complement, n_r equals 00010001. R equals 2, n equals 8. z_r equals 11,111,111. n_r equals 11,111,111 equals 11,101,110. What is the simple approach to 1's complement? Comparison of binary sign magnitude, binary 2's complement, and binary 1's complement formats. Real numbers in signed binary numbers can be represented in fixed point or floating point. The location of the radix point is agreed upon in fixed point, while in floating point, the location of the radix point must be decoded. Any real number should be reformatted and normalized such that the first digit is a 0. For example, 123.456, 10, equals 0.123456 times 10 to the 3e equals 3. 123.456, 10, equals 0.0001234556 times 10 to the 6 in a 6 decimal point fixed point number e equals 6. The standard for representation is a 32-bit word. The MSB represents the sign. 1 equals negative, 0 equals positive. The next 8 bytes represent the exponent, and the last 23 bits represent the mantissa. The estimation of the value is 1 caret sx1, mx2 caret e127. The standard for representation is a 32-bit word. The MSB represents the sign. 1 equals negative, 0 equals positive. The next 8 bytes represent the exponent, and the last 23 bits represent the mantissa. The estimation of the value is 1 caret sx1, mx2 caret e127. For example, 123.4510 equals 10,011,010.1010. 2 equals 1.0011010010 x2 to the power of 9. 10 plus 127 equals 137 equals 10,000,001. For example, 3.5, 10, equals 11.1, 2 equals 1.1 x 2 to the power of 2, plus 127 equals 128 equals 10 million. For example, 3.5, 10, equals 11.1, 2 equals 1.1 x 2 to the power of 1, plus 127 equals 128 equals 10 million. Another example, 3.1, 10 equals 11.00011001100011, 2 equals 1.10001100110011, x2 to the power of 1, plus 127 equals 128 equals 10 million. The value actually stored is 3.09999046325683599375, with an error of 9.5367431640640625E8.